Now let's try and do some review of work, power, and energy. Now make sure you remember your formulas. Work is defined to be a force through a distance. And remember, we measure work in joules. Power is work divided by time. We measure power in watts. We have two kinds of energy, two kinds of mechanical energy we worry about in this class. The first kind is kinetic energy, and kinetic energy has to do with motion. That's 1/2 times the mass times the velocity squared. And again, we measure kinetic energy in joules, and because this is squared, kinetic energy is always positive. We have two kinds of potential energy. The first kind is due to gravity, and that's just mgh. Again, the units for potential energy are joules. Now, potential energy can be positive or negative, depending upon where you define your 0 to be. So if I take the ball and I define this as y equals 0, so that h is positive here, if the ball drops below your 0, then this will be a negative. So you can have negative potential energy, but it's only negative when you put it in a well. And then the other kind of potential energy we have is spring potential energy. And I usually just put a little SP down here. And this is 1/2 kx squared, and our units are joules. Now remember, K is a spring constant, and that's measures the stiffness of the spring. And make sure you measure K in newtons per meters. You've got to make sure you do that conversion to newtons and meters. And x is the distance from its relaxed state. So this is the displacement from equilibrium. And of course we have to measure this in meters. So a picture of a spring would be, say we have a block and we have a spring, and say it's stretched out. If this is equilibrium point, this distance right here will be delta x. Now, spring potential energy is always positive. You can't have a negative spring potential energy because it's x is squared and k is positive. The only thing I can really trip you up here is if I give you work is FD. Let's just look at this. If you lift something up, all right, remember work is positive if the force and the displacement are in the same direction. So if they're both going up, both going to the right, both going to the left, or both going down. Another way to tell if work is positive if it's speeding up. All right, an example of this is a dropped ball. You're pushing a table with a constant force in a direction. Work is negative when the force is in the opposite direction of the displacement. Friction is an example of a force that is always negative. Gravity sometimes does positive work and sometimes does negative work. Remember, the force due to gravity is always pointed down. So when your displacement is up, gravity does negative work. While over here, force points down, displacement points down. When a ball is falling, gravity does positive work. The last real concept we have is conservation of energy. And a lot of times I abbreviate this conservation of energy. Suppose I have a pendulum bob that is up a height h. We know at point 1 it's all potential energy, and at point 2 at the bottom it's swinging down as fast as it can. It's all kinetic energy. So conservation of energy tells me the kinetic energy at 1 plus potential energy at 1 has to equal the kinetic energy at point 2 plus potential energy at point 2. Suppose I have a roller coaster. All right, and say it has some humps in it. Then conservation of energy tells me that if this is point 1 right here, then the kinetic energy at point 1 plus the potential energy at point 1 has to equal, say, the kinetic energy at point 2 plus the potential energy at point 2. It also has to equal the kinetic energy at point 3 plus the potential energy at point 3. Say if you're on a point right there, if that's point 3. We'll always give you enough information to find this. And let me point out that in these problems, the masses will always cancel. So let's just look at, say, this right here. Say the masses don't cancel. Or let's just write out what this means. Kinetic energy at point 1 is 1/2 times the mass of the object times its velocity at point 1 squared, plus potential energy at 1, which is a mass, times gravity, times whatever this h1 is. This has to equal 1/2 mass. Now the kinetic energy at 2 is going to be the velocity at 2 squared, plus mgh at 2. Look what happens. I can divide this whole thing. Every term has a mass. So we can divide out the masses. So if I don't give you the mass, you really don't need it. It will cancel. You do need the mass to find the total energy. But when we're looking at these relationships, remember, sometimes, or actually usually, at least one or two of these will wind up going to 0 so that you can get a very simple relationship. Now, let's look at some of the true-false questions. For work to be done on an object, an object must have moved a distance due to a force exerted on it. That's kind of the definition of work, isn't it? Work is FD. So this one is true. You are limited by your power output, not by the amount of work you can do. Well, let's think about this. Remember when you were climbing the stairs? All right. The faster you went, okay, since power is work divided by time, remember the work you did was the same. It's this time right here that got you. So this one is also true. You are limited by your power. I mean, I guess, yeah, technically you are limited by the amount of work you could do. But the limiting factor between work and power is going to be power. So this one's true. Energy is a conserved quantity. Yep, conservation of energy. That's what we've been talking about. Energy cannot be created or destroyed. The work done on an object is equal to its change in gravitational potential energy. Sure, work is a change in potential energy. Okay, imagine the work done to lift a block, a height h above a table. All right. Now, don't let this one throw you because work is also the change in kinetic energy. Basically, work is a change in energy. So this one is also true. Fill in the blanks. Work is a blank quantity in which direction doesn't matter. Now, when we're talking direction, now we're bringing up vector versus scalar. So this is a scalar. The units for work, that's joules. Remember, if you work, you can afford to buy joules. If positive work is done on an object, the force must be applied in the blank direction as the distance the object moves. Let's see. The force and the displacement have to be in the same direction. If blank work is done on an object, the force was applied in the opposite direction. Do you remember what this was called? If the force and displacement are in opposite directions, this is going to be the opposite of positive is negative. A common force that causes negative work to be done on an object is, well, the force that always causes negative work is, of course, friction, because friction opposes motion. What is power? Power is the rate at which work is done. Okay, a formula is power is work divided by time. Remember, whenever there's time in the denominator, we're talking about a rate. The units for power are what? You're right, watts. I should have written joules out, shouldn't I? We abbreviate it with J. We abbreviate watts, capital W. Please, on your test, do not write JEWLS. I know that's funny, but get credit. Multiple choice. Okay, the further an object gets from the Earth's surface as it is thrown upward, the gravitational potential energy is, well, it's greater. It's got to be more. Because if this is the surface of the Earth and you're measuring H, gravitational potential energy is mgh. If positive net work is done on an object, the object's kinetic energy is it increasing, decreasing, staying the same, or zero? Since work is equal to the change in kinetic energy, if work is positive, the kinetic energy has to be increasing. If negative work is done on the object's kinetic energy, well, has to be decreasing. Kinetic energy is only found in objects that are, let's see, still and at rest are the same answer. So you know you've got to check those. And of course, kinetic means moving, so the answer is C. If a car starts moving 4 times faster, what's the new kinetic energy? Okay, write out the formula. KE is 1/2 mv squared. Now you're going to go 4 times faster. So 4 is the speed, and when I square 4, I get that it is 16 times faster. Now let's try some problems. If a neighbor pushes a lawnmower 4 times as far as you do, but exerts only half the force, which one of you does more work and by which? Okay, let's look at this. Let's look at the work your neighbor does. A neighbor pushes a lawnmower 4 times as far. So the distance the neighbor pushes is 4 times the distance you push it. All right, so this is D and this is F. So let me tell you what, let me start this one over. Okay, let's do this one in colors. I like this one. Let's say the distance the neighbor covers is this. This is the distance of the neighbor. And he pushes it 4 times as far as you do. So I'm going to put you in red. So this is about the distance you cover. Okay, but he exerts only half the force. So basically, let's put the forces down here. You exert twice the force as your neighbor. All right, I'm going to come over here and put these in black now. So the distance of the neighbor is 4 times the distance of you. And the force of you is twice the force of your neighbor. Did I do that right? Yeah, he did half the force, so you did twice. Who does more work? Well, work is FD. Let's look at this. The work you did is your force, this is you, times your distance. So, we need to solve this right here for the force of the neighbor. The force of the neighbor is 1/2 the force of you. All right, the work of the neighbor is the force of the neighbor times the distance of the neighbor. So let's plug in the force of the neighbor is 1/2 times the force of you. The distance of the neighbor is 4 times the distance of you. Okay, 4 divided by 2 is 2, the force of you, distance of you. So this is twice the work of you. So the neighbor still does twice your work. A 50-kilogram student climbs a 5-meter rope at constant speed. If the student's power is 200 watts, how long does it take the student to climb the rope, and how much work does he do? All right, draw diagrams. All right, here's the student, and he's going up. D is up. Let me start writing some stuff down. Let's see. Let's go with, let's not do that. Let's erase. The mass of the student is 50 kilograms. You'll find if you always just go on and write things out, it makes life easier. That's your mass. He climbs 5 meters up a rope. This is going to be your distance at constant speed. If the student's power is 200 watts, so P is 200 watts, how long will it take the student to climb the rope, and how much work does he do? Let's first find his work. Work is force through a distance. Now, what force is the student having to apply? Well, when I do my free body diagram, I see that the force, because we're at a constant speed, the force has got to equal his weight. So this is mg times d. So his mass is 50 kilograms. Gravity is 9.8 meters per second squared. And the distance covered is 5 meters. So this becomes 2,450 joules. So he does 2,450 joules of work going up. So now power is work divided by time. So to find the time, I have power and now I have work. So this is straightforward. I'm going to go through the steps of solving this. Time is in the denominator, so I want to get rid of it. I'm also looking for it. So I'm going to multiply both sides through by time. So PT is equal to, those two times cancel, it's equal to the work. But folks, I'm still looking for time. So I'm looking for time because I'm multiplying by P. I'm going to divide both sides through by P. So the time is the work divided by the power. The work done is 2,450 joules. The power exerted is 200 watts. So the time is, let's see, did I do that right? 2,450 divided by 200 is 12.25. seconds. So there are my two answers. Can the speed of an object change if the net work is 0? Well, if the net work is 0, what does that mean? That means the change in kinetic energy is also 0. Well, what does the change in kinetic energy look like? It's 1/2 mv final squared minus 1/2 mv initial squared. Now I'm going to come through and factor out this 1/2 m. So this is 1/2 m v final squared minus v initial squared. Now the only way for can the speed of an object change? Okay, so the only way for these to change is for this to not be 0 is if these are not the same. So in order to have a speed change, you must do work. So the answer is no. Sorry. Okay, a person lifts a 4.5 kilogram cement block. So M is 4.5 kilograms. A vertical distance of 1.2 meters. So D is 1.2 meters. Find the work done by the person. Draw your free body diagram. Now, obviously, this is the work, this is the force done by the person. The force has got to equal the force of gravity. So work is FD. The force he's overcoming is the weight. So this is mgd. The mass is 4.5 kilograms. G is 9.8 meters per second squared. And D is 1.2 meters. Multiply that out and you get 53 joules. If an automobile engine delivers 37,300 watts of power, how much time will it take for it to do 640,000 joules of work? All right, write out your givens. Don't panic. These are some big numbers. Watts. Watts are power. And it also says of power. So power is 37300 watts. And the work is 640. Go on and put your commas in. Keep yourself straight. How much time? So we're looking for T. So my equation, power is work divided by time. Now I need to solve this for time. So I'm going to circle time in red. Well, I was going to circle it in red. I want to get rid of time because it's in the denominator. So to get rid of anything in the denominator, I multiply both sides by it. Those two cancel. So I'm left with work is PT. But I'm still looking for time. So because I'm multiplying by power, I need to get rid of it. I need to divide. So the time is work divided by power. So now I can come up here and plug my numbers in. The time it's going to take is the work, which is 640,000 joules, divided by the power, 300 watts. And when you multiply this out, all right, you get 17.2 seconds. A grocery cart is pushed 12 meters along an aisle by a shopper who exerts a constant horizontal force of 40 newtons. How much work is done? Draw your diagram. He's pushing horizontally, and your displacement is also horizontal. So D is 12.0 meters. Put your decimal there. Force is 40.0 newtons. Okay, I'm looking for the work. That's my unknown. Work is FD. So the force is 40 newtons. D is 12 meters. 40 times 12 is 480 joules. Now, a motor-driven winch. Now, a winch is just a device that helps move things. Pulls a 50-kilogram student 5 meters up a rope at a constant speed. Okay, here's my mass. 5 meters. This is my distance. And I have a speed of 1.25 meters per second. How much power does a motor use in raising the student? Let's look at our formulas. Power is equal to work divided by time, but I don't have that. I also know power is equal to the force applied times the speed. So let's write out our givens. The mass is 50 kilograms. The displacement is 5 meters. And speed is 1.25 meters per second. Having trouble with my decimals here. So I want to use power as FV. But what's the force it's applying? Well, the force it's applying has to be, of course, the weight of the student. So this is mg, that's the force, times v. So the mass is 50 kilograms. G is 9.8 meters per second squared. and V was 1.25. All right, so it has a power, exerts a power of 612.5 watts. How much work does the motor do on the student? Well, the work is, of course, the force times the distance. So the force is mg d. The mass is 50 kilograms. G is 9.8 meters per second squared. And, oh goodness, I don't have a distance. Goodness, what do I do? Oh, I do have a distance. The distance is 5 meters. Sorry. See, teachers get confused too. Don't ever feel bad about making mistakes. We all make mistakes. Some of us just do it while we're recording ourselves. So 50 times 9.8 times 5 is 2,450 joules. All right, a student of mass 80 kilogram runs up 3 flights of stairs in 12 seconds. The student has gone a vertical distance of 12 meters. How much work? Determine the amount of work done by the student to elevate his body to this height. Well, let's see. Mass is 80 kilograms. Time is 12 seconds. And then D is 8 meters. Go on and remember the diagram from the lab. Okay, this is the distance you covered. Here you are, you're happy, you're down here, you're smiling, then you run up, and then you're out of breath. You're tired at the top. The work done is the force times the distance. And remember, it's always a vertical distance when we're talking about raising and lowering objects. Now, what force are we overcoming? Here you are. What's the only force acting? And of course, that's Fg. You're overcoming gravity. Okay, so this is mg d. Your mass is 80 kilograms. Gravity is 9.8 meters per second squared. And your displacement is 8 meters. So this becomes 6,272 joules. What power is exerted? Well, let's see. Power is work divided by time. Your work was 6,272 joules, and your time was 12 seconds. So you get 522.7 watts. That's a watt. That's a terrible watt. Let me erase that. Try again. What amount of work can a 600 watt electric drill do in 240 seconds? Let's see. Givens, power is 600 watts. Time is 240 seconds. So let's see. Power is work divided by time. All right, I want to solve this for work. Okay, so I want to get rid of my fractions. Get rid of my fractions and multiply through by t. So PT is equal to work. Wow, that's kind of cool. All right, let me switch colors here. So the work done is going to be the power times the time. I just want them in black. The power is 600 watts. The time is 240 seconds. So the work done is going to be 144,000 joules. All right. A 40 kilogram boy runs up a staircase to a floor 5 meters higher in 7 seconds. What's his power? Well, this is the same situation. All right, here's his distance. Here he is. I don't know why I like this diagram, but I just do. So the mass of the boy is 40 kilograms. D is 5 meters. Time is 7 seconds. Power is work divided by time. And of course, the work is force times distance divided by time. And the force he's overcoming is gravity, which is mg d divided by time. So the mass is 40 kilograms. G is 9.8 meters per second squared. And the distance he covers is 5 meters vertically, divided by his time, and his time is 7 seconds. So you get a power output of 280 watts. Now what's the kinetic energy of a 50 kilogram boy sprinting at 7.5 meters per second? Mass is 50 kilograms, and your speed is 7.5 meters per second. And of course, we're looking for the kinetic energy. So let me come up here. Kinetic energy is 1/2 mv squared. So this is 1/2 the mass of 50 kilograms. The velocity is 7.5 meters per second squared. Now this is very important. When you do these, go on and square the 7.5 first. So this is going to be 1/2 times 50. 7.5 squared is 56.25. Once you've done that, go on and multiply by 50 and then divide by 2 to get 1,406.25 joules. You know what? That's messy. Let me write it over. 1,406.25 joules. What's the gravitational energy of a 75 kilogram man on the 3rd floor, 10 meters above the Earth's surface? Okay, so here we are. This is the man, and here's his height. Okay, I know he's a little square, but that's okay. Sorry about the bad pun. His mass is 75 kilograms. Does it matter that he's on the 3rd floor? No, that's not one of our more scientific terms. We're worried about the 10 meters. So his height is 10 meters. All right, we want his potential energy. Potential energy is mgh. Gee, is this looking like anything? Of course, it's looking like the work done to raise it, because the work is equal to the change in potential energy. Okay, mini lecture over. All right, mass is 75 kilograms. G is 9.8 meters per second squared. And he's lifted a height of 10 meters. So the potential energy of this young man is 7,350 joules. Now, a spring has a constant of 1,000 Newton meters. So K, my spring constant is 100, I said 1,000, I meant 100, newtons per meter. Check it, Newton meter, we're in good shape. If the spring is compressed, okay, so here is the spring when it's nice and happy. And it's compressed, and compressed just means it's squished, 0.08 meters. So delta X is 0.08 meters. What's the elastic potential energy? Well, the elastic potential energy of a spring is equal to 1/2 K delta X squared. So it's going to be 1/2 times 100 times 0.08 squared. Now this is important. Make sure you square the 0.08 first. So this is 1/2 times 100. Now you don't have to write this step in, but if it confuses you, I would recommend you do. 0.0064. That is 0.08 squared. Now 0.0064 times 100 divided by 2 gives me 0.32 joules. What is the gravitational potential energy of a pendulum that hangs 1 meter above the ground and has a mass of 1.5? Okay, guys, we've got the pendulum and it's above the ground. So we're looking at this height here. So h is 1.0 meter and the mass is 1.5 kilograms. Gravitational potential energy is mgh. So the mass is 1.5 kilograms. G is 9.8 meters per second squared. And the height is 1.0 meter. 1.5 times 9.8 times 1 is 14.7 joules. All right, assume the law of conservation of mechanical energy holds true. It always does. Calculate the velocity of a roller coaster at the following points. Oh my gosh. All right, let's do a diagram. The roller coaster has a starting at a hill 50 meters above and a second hill that is 25 meters. Oh gosh. If the car starts from rest, what's its velocity at 31.3 or at the bottom of the first hill? Okay, draw your diagram, folks. Let's label this point A and this point B. I'm going to label this point right here C. Now I'm going to put in this as my zero height. This is h equals 0. All right? This is my 0. Remember, you can always pick your origin anywhere you want. Pick it somewhere smart. I recommend you make a chart. Let's see. At point A, just put A and put a line here. The roller coaster starts at a hill that's 50 meters tall. So this height, this h1, is 50 meters. Okay. B, what's the height at B? Let's call it HA here. HB is 0. And then at C, HC is 25 meters. If a car starts from rest, so starting from rest, it's starting up here. That means the velocity at A is 0 meters per second. What's its velocity at the bottom of the first hill? So we want the velocity at B. Now, please don't let the equation scare you. Let's see. We have the total energy at A has to equal the total energy at B. All right, you know that. The total energy at A has to equal the total energy at B. Now, I'm going to write all this out, and you need to do it as well on your test. The total energy at A is the kinetic energy at A plus the potential energy at A. And this has to equal, we're looking at point B, so the kinetic energy at B plus the potential energy at B. Now we put our variables in. The kinetic energy at A is 1/2 mass times the velocity at A squared plus mg h at A. And this has to equal 1/2 m kinetic energy, velocity at B squared, plus mg h at B. Now, go on and mark out what's 0. I know V at A is 0, so this whole term is 0. I know H at B is 0, so this whole term is 0. Let me rewrite this. Let me put this in another color so you can see it. mgha equals 1/2 mvb squared. Now, folks, we're looking for the velocity at B, so we need to solve this. Let's see. Is it straightforward for you to see that there's a mass on both sides? So these are going to actually cancel. Now the next step, we want to get rid of this 1/2. So we're going to multiply both sides through by 2. So 2g h at A is equal to, those cancel, vb squared. I want the velocity at B, so I need to square root both sides. I'm going to come over here and use a different color so we can kind of see it. So the velocity at B is going to be the square root of 2g times the original height. All right? So the velocity at B is the square root of 2 times 9.8 times 50. Go ahead and multiply all this out. 2 times 9.8 times 50 is 980. And now square root 980, and you get 31.3 meters per second. Now part B is asking at the top of the second hill. Let's go ahead and redraw this. All right. This is H at A, and this is H at C. Let me go on and redo this. At A, and I'm just going to compare A and C because I really don't care about B at this point in time. This is point A and this is point C. B is down here. We've already done B. I always write all my givens down at the very beginning. Remember, like I did over here, going to write them all down to start with. For parts B and C of a problem, you don't need to rewrite them. We're rewriting because we're on another page. All right. At A, I know the height at A is 50 meters. I know the height at C is 25 meters. And I know the velocity at A is 0. And I'm looking for the velocity at C. Let's see how the energy formula changes. I know the energy at A has to equal the energy at C. Now, I know it's a lot, but let's just go on and write it out. So I know the kinetic energy at A plus potential energy at A has to equal the kinetic energy at C plus the potential energy at C. The kinetic energy at A is 1/2 mVA squared plus the potential energy at A is mgh at A. This equals the kinetic energy at C, 1/2 mvc squared, plus potential energy at C, which is mgh at C. All right, is there anything I can make 0? I know the velocity at A is 0, so this whole term can go to 0. But nothing else is 0. So, let's see. Can we cancel out the masses? I do have a mass in each term, so I can cancel my masses out. And the only time you can cancel is when it is in each and every term. Let me rewrite this. So, G H at A is equal to 1/2 VC squared plus GHC. I'm looking for what? VC. Let me go on and subtract GHC from both sides. I know I didn't clear fractions just yet, but you'll forgive me when I show you why in a second. So this is G times HA minus GHC is equal to 1/2 VC squared. Now I'm going to get rid of the 2 by multiplying both sides, hug the whole equation, and multiply through by 2. So the 2's cancel. So VC squared is equal to 2. Now, do you mind if I factor this G out? I'm going to factor that G, H at A minus H at C. All right, I'm going to come up here and rewrite this. I need to square root both sides. Now, do you see the velocity at C is going to equal the square root of 2G times HA minus HC. Do you see this is the height that it winds up dropping? All right, isn't this cool? This is actually HA minus HC. I love math. Math is a lot of fun. If you get something very complicated that's not symmetrical, that's just awful, you've probably made some sort of algebra mistake in here. If you've got M's everywhere, erase, start over, clean your math up, because these problems will simplify into beautiful, easy mathematics. All right, so VC is the square root of 2 times 9.8 times HA, which is 50 meters, minus 25. Now go on and do that subtraction. It's the square root of 2 times 9.8 times 50 minus 25 is 25. Once again, go on and put this in your calculator. 2 times 9.8 times 25 is 490. So this is the square root of 490. And when I square root that, I get 19.8 meters per second. Common sense test. Does it pass common sense test? This is less than the speed at the bottom of the first hill. So good. If you'd gotten a speed faster, well, that's not good. You know you'll have made a mistake. Go back and check. All right, starting from rest, I just told you the velocity to start with is 0. A 20 kilogram child zooms down a frictionless slide at an initial height. If the speed at the bottom is 3.8 meters per second, how high above the ground did she start? Now look at this, folks. This is basically the same problem we just did. This is point A, this is point B. Here's the height at A. And you're going to be smart and put your 0 here. So, 2 points, A and B. Now, I know the mass of the child is 20 kilograms. I'll write that in a second. I'm looking, let's see, H of A is, I don't know, that's what I'm looking for. H at B is 0 because you were smart and you chose it to be the equilibrium point. Now, it starts from rest. This tells me the velocity at A is 0. And at the bottom, she's going 3.8 meters per second. So the velocity at B is 3.8 meters per second. How high above the ground does she start? So we're looking for this. All right. I told you the mass is 20 kilograms, but hint, you're never going to need it on these problems. I know the energy at A has to equal the energy at B. The energy at A, I know it's long, but let's write it out. It's kinetic energy at A plus the potential energy at A has to equal the kinetic energy at B plus potential energy at B. Okay, the kinetic energy at A is 1/2 m, the velocity at A squared, plus potential energy at A, which is mg h at A. This has to equal the kinetic energy at B, which is 1/2 m, velocity at B squared, plus potential energy at B, which is mg h b. At this point in time, come through and make your zeros. I know the velocity at A is 0, so this whole term goes to 0. I know the height at B is 0, so this whole term goes to 0. I just love doing that. Isn't that fun? Now, I see I have a mass in each term, so those will cancel. So I have G, height at A, is equal to the velocity at B squared divided by 2. Remember, 1/2 VB squared is the same thing as VB squared over 2. Those are equivalent. So for H of A, I need to divide both sides through by G. So the height of A is the velocity at B squared divided by 2G. Now we can plug in. This is 3.8 squared divided by 2, 9.8. Go on and multiply these out. All right, 3.8 squared is 14.44. Okay, 2 times 9.8 is 19.6. 14.44 divided by 9.6 is 0.74 meters. A toy dart gun has 45 joules of potential energy. Well, that's easy. Potential energy is 45 joules. When the dart is compressed and ready to fire, how much kinetic energy does the dart have immediately after it's shot, and why? Oh, hold on. Okay, I'm going to draw, a gun. I'm so sorry. Here's the spring, and it's coiled. Here, it's all potential energy. As soon as I fire it, the spring is released, and it is all kinetic energy. So if the potential, I know from conservation of energy, the energy when it's compressed has to equal the energy after it's shot. Conservation of energy. So if the energy when it's compressed is 45 joules, when it's shot, it also must be 45 joules. You could have just said conservation of energy, COE. All right, if a roller coaster has 0 velocity at A, what must its speed be at B? Now we've done one very similar to this. Make a chart, A, B. The height at A is 5 meters. The height at B is 3 meters. And it has 0 velocity at A, so the velocity at A is 0, and we're looking for the velocity at B. We know the energy at A must equal the energy at B. So the potential energy at A plus the kinetic energy at A has to equal the potential energy at B plus the kinetic energy at B. The potential energy at A is mg HA plus 1/2 m velocity at A squared. This is equal to the potential energy at B, which is mg h at B, plus the kinetic energy at B, which is 1/2 m velocity at B squared. Now come through and put in your zeros. Velocity at A is 0, but that's the only thing that's 0. Next, come through and see if we can cancel our masses, and lo and behold, yes, we have a mass in every term, so the masses cancel. So I'm looking now for the velocity at B squared. So why don't I rewrite this? GHA is equal to GHB plus velocity at B squared over 2. I'm trying to get the velocity at B by itself, so I'm going to subtract GHB from both sides. That's a B there. It doesn't look like it. So this is G. I hope you don't mind. I'm going to go and factor this. HA minus HB. I could have written this separately. This is velocity at B squared over 2. Those cancel. I want to get rid of the 2. So I'm going to come through and multiply both sides by 2. And then I'm going to rearrange this. The velocity at B squared is 2G times the height at A minus the height at B. Now I'm having trouble seeing this, so I'm going to switch colors after I square root. So I'm going to come up here. The velocity at B is the square root of 2 times 9.8 times the height of A is 5 minus the height of B is 3. Go on, and this is 2 times 9.8 times 2. Go on and do this calculation under the radical. 2 times 9.8 times 2 is the square root of 39.2. Is that right? Let's see. 2 times 9.8 times 2 is, yep, 39.2. And the square root of 39.2 is 6.24. Oh my gosh, imagine that. I made a mistake. This is, 6.26 meters per second. Ah, wrong answer, folks. Wrong. Happens. You'd have lost a point on the test for popping out the wrong answer. But let me talk about how I would have graded this. Okay? You're going to get 2 points for getting all these givens in the right order. You're going to get a point for writing this equation and then a point for writing this equation. You're going to get a point for doing, you might get 2 points for all this algebraic solving, a point for plugging in, all right, a point for your answer, and a point for your units. 2, 3, 4, 5, 6, 7, 8. So this probably would be worth a good 8 points. All right, What are the 6 types of energy we discussed? Well, those were mechanical, which remember is the energy behind things that are moving. Radiant, that's the waves. Chemical, this is the stored energy. Food and fuels. Heat, this is our thermal energy. Electrical, we're going to do a whole unit on electricity. And nuclear, this is fission and fusion. Mechanical energy is the sum of what 2 types of energy? Potential and kinetic. All right, the units for energy. Energy is joules. You don't have to worry about writing it out, just put a big G. What does the work energy principle tell us? Work is the change in energy. All right, work may be the change in kinetic energy, or work may be the change in potential energy. Basically, it takes work to change the form of energy. That's probably the best way to put it. It takes work to change energy forms. So from chemical to mechanical to thermal, say. What are the 2 types of potential energy we discussed? Well, that's gravitational potential energy and spring. What's the difference? Well, gravitational is due to position, S-I-T-I-O-N, above the Earth. Spring has to do with compressing a spring, of course, compressing or stretching. The best way to describe them is probably potential energy for gravity is mgh, and the spring is 1/2 k x squared.